Welcome to this explainer. Today we're going to act like neutron detectives. We are diving deep into the core of a nuclear reactor to track the generational population of neutrons and really decode the complex math behind the 4 and 6 factor formulae. Basically, we're going to break down exactly how a reactor actually sustains its chain reaction.
Here's our roadmap for today. 1. The perfect generation balance. 2. Neutron life cycle hazards. 3. Infinite versus finite reactor models. 4. The reproduction factor. And number 5, the fast fission boost. Let's jump right in.
Starting with Section 1, the goal, which is achieving that perfect generation balance.
Okay, so the ultimate goal for any thermal reactor is basically extreme population control. Engineers have to maintain a perfectly balanced neutron population from 1 microsecond to the very next. And to do that, we rely entirely on this one simple but absolutely crucial equation, K equals 1. The variable K represents the ratio of the number of neutrons between 2 successive generations. If this number drops even a little bit below 1, the population shrinks, and the reactor just kind of fizzles out. But if it creeps above 1, you're looking at an exponential runaway reaction.
When K is exactly 1, right on the money, we hit a steady state known as criticality. For a reactor to achieve this, the exact same number of thermal neutrons must survive into generation 2 as there were in generation 1. It's a perfect, continuous loop. Simple in theory, right? Well, in practice, it's a whole different story.
Which brings us to Section 2, the hazards of the neutron life cycle.
Making sure just one neutron survives might sound easy, but man, it is a dangerous world out there for a newborn thermal neutron. Every single time a neutron is born from a fission event, it has to run this massive gauntlet of hazards that could wipe out the population before the next generation even begins. I mean, first, it could suffer radiative capture, where it's absorbed by the fuel but doesn't actually cause a fission. Then, because neutrons are born moving insanely fast, they might just leak right out of the reactor core while they're fast, or even leak out later after they've slowed down. And if that wasn't enough, they could just be uselessly absorbed by non-fissile alloy structural materials inside the core.
Take a look at the specific hazard highlighted here in our source material. This is resonance capture by fertile nuclides, like uranium-238. You see, as our fast neutrons are slowed down by the moderator, their absorption cross-section increases. And uranium-238 has literally hundreds of these capture resonances in the EV to keV range. Think of them like specific energy traps that just eat up our slowing neutrons, with absolutely zero chance of causing a fission. And since the proportion of this fertile U-238 is way higher than the actual fissile fuel, it heavily reduces the number of neutrons that successfully reach thermal energies.
All right, moving to Section 3, infinite versus finite reactors. Because of all these wildly specific hazards we just talked about, physicists actually use 2 different mathematical frameworks. First, they model what's called a notional infinite reactor. It's exactly what it sounds like. If we imagine a theoretically infinite reactor core, well, those leakage hazards just don't exist. The neutrons literally have nowhere to leak out to. In that ideal made-up scenario, the math relies on the 4-factor formula. But we live in the real world, and real-world reactors are finite. They have physical edges. So, to account for the probability of neutrons leaking out of those boundaries, physicists have to expand the math and use the much more complex 6-factor formula.
Let's dive into Section 4, the reproduction factor.
So now that we've looked at the terrifying gauntlet of hazards that kill neutrons off, let's look at the factors that actually govern neutron births. Section 3.2.8 of the text highlights a super important distinction. Neutron absorption absolutely does not guarantee fission. Only a portion of the neutrons absorbed in the fuel actually trigger a splitting atom. The rest, just captured, gone. Because of this reality, we have to define highly specific variables to accurately calculate our actual neutron birth rate.
The text actually throws a really great pop quiz at us right here to test this exact concept. It asks us to differentiate between the Greek letters nu and eta. It asks, which one is greater in magnitude and why? Take a second to think about it. What actually happens when a neutron hits the fuel?
Well, here's the deal. The answer comes down to the harsh reality of those parasitic absorptions we discussed earlier. Nu represents the average number of neutrons produced when an actual fission successfully occurs. But eta is the neutron reproduction factor, meaning it's the net number of neutrons produced per neutron just absorbed in the fuel. Because of this, eta is strictly less than nu. Why? Because eta has to account for all those times a neutron is absorbed by the fuel but completely fails to cause a fission. It's basically the difference between the ideal birth rate of a successful split and the actual effective birth rate every time a neutron just hits a fuel rod.
And that brings us to Section 5, the fast fission boost.
Okay, so if eta is lower than nu, and our neutrons are constantly being lost to resonances and leakage all over the place, how on earth do we maintain that perfectly balanced k equals 1? Well, fortunately, the population gets this amazing, unexpected final boost, the fast fission factor, represented by the Greek letter epsilon. Now, generally, we need to slow neutrons down to thermal speeds to get fission, right? But it turns out some newly born incredibly fast neutrons actually cause immediate fissions while they are still in the fast region. They smack into both fissile U-235 and fertile U-238 before they even hit the moderator. This gives us a vital, much-needed population bump to offset all our losses.
Mathematically, this fast fission factor is defined as the ratio of total fission neutrons to thermal fission neutrons. Looking at the math here, it's a baseline of 1 plus a bonus ratio of the neutrons produced in fast fissions divided by the neutrons produced in thermal fissions. It is quite literally a mathematical multiplier representing our high-speed bonus births.
Now, the source text gets into some pretty heavy integral equations to map out these fast and thermal ranges precisely. But honestly, the most crucial takeaway is this concluding note right at the bottom. For every single thermal neutron successfully absorbed in the fuel, exactly eta times epsilon fast neutrons are pumped right back into the reactor. And then, the entire life cycle starts all over again.
Think about what we just tracked: the specific birth rates, the parasitic deaths, the resonance energy traps, the physical leakage, and finally, the fast fission bonuses. Which leaves us with this absolutely mind-bending thought to close on. Knowing all of these wildly distinct, volatile, microscopic factors, how incredibly precise must the physical engineering, the material purity, and the geometrical layout of a nuclear core be to consistently guarantee that this generational population balances to exactly, perfectly, k equals 1? It is a true marvel of applied physics. Thank you so much for joining me on this explainer, and keep questioning the science around you.